So it's really, if you know the history of soap has been invented like 5,000 years ago.
What?
And there are some historical things, there are some controversies who first made it, whether it's the Roman or Babylonian or Venetians. But we're not going to go to the history. But what they really used to do is to use animal fat and wood ash and then heat it, essentially boil it. And that made the soap. So to understand the mechanism of this, really, the animal fat is typically made mostly of triesters of glycerol. Now glycerol is actually 3 hydroxyl groups, CH2OH, CHOH, and CH2OH. So this is glycerol. And the triesters, of course, will have OCOR. So that glycerol, if you convert it to triesters, OCOR, CHOCOR prime, and CH2OCOR double prime. So the R groups could be different or the same. But typically the R groups here are very, very long chain hydrocarbons. So R prime and R double prime are long chain hydrocarbons. So what really happened is that the wood ash contains K2CO3, which is a weak base, and that really hydrolyzed the esters. So after the hydrolysis, what you get is glycerol, of course, but also you get the carboxylate anion or sodium or potassium salt of this long chain fatty acid, RCOOK, R prime, COOK, and R double prime, COOK. So these long chain salts. Now, if you consider any of these which has a really very long chain of hydrocarbon, and at the end you have a CO, O minus, K plus. So one of the property of this type of compound is that you have a very long chain which is hydrophobic. And then at the end, you have a salt which is hydrophilic. So in the same compound, then you have one part that loves water, the other part that hates water. And so what they normally do, if you drop that in water, they are going to form what we call micelles. Micelles are, you have like a head group which is water loving, that will be exposed to the water, and then you have a long chain. And they will generate this type of pore So essentially it generates something like this, where the head groups or the carboxylate anions are exposed to the water. Okay, that can interact with water. The inside core avoids water as much as possible. That's why they aggregate like that. And what they can also do, they are fat soluble, therefore they can trap fat in there, fat or anything. So if you have grease or fat, they would be trapped here, and that's how essentially the soap really works. It just takes away the grease by acting with that. And so that is really the micellar properties of the soap, which was really related to ester hydrolysis. Any question on that? All right, so let's go to the practice exam, and we can point out certain things relevant. Okay, so the first question, of course, relate one particular knowledge for you. Okay, the acid base, which is very chapter 1, but you need to have a general idea what the acidic properties of different compounds are. For example, the acids, we can break it down into several groups, and unlike the very first exam, when I gave you the pK values, I'm not going to give you the pK values anymore. Okay. Too bad. Now you have to know some of the basic properties. So let's look at some of the compounds that we dealt with and what they really are. Okay, so hydrocarbons. Okay, so the alkanes typically have the pK values above 650. So it's anywhere between 50 to 65, somewhere in that range. Very, very high pK. Alkenes, and when you say alkene, of course the one that I'm talking about, it may be a long chain, but the one that's relevant is when you have sp2 carbon attached to the hydrogen. So this is the one that is relevant. The pK of this proton is somewhere in the 40s. And that is typical for other sp2. If you look at aromatic compounds like benzene and so forth, this hydrogen is also in the 40s. And then if you go to alkynes of the hydrocarbons, that is the most acidic, where you have a carbon-carbon triple bond, this hydrogen is about 26. And so you should be able to figure this out from the hydrocarbons that they are, if it is alkane hydrogen, sp3 hybridized carbon, joined with hydrogen, that is above 50. If you have alkenes, they're around 40. If you have alkynes, they're about 26. Okay. Now, alcohols and waters have approximately the same pK, which is about 16 to 18. Carboxylic acids are much more, although we did not actually cover the chapter of carboxylic acid. But you still need to know that carboxylic acids are typically between 2 to 5. Acetic acid is roughly about just below 5. And that's very typical of carboxylic acid. If you look at other types of compounds, the ones that we talked about is ammonia, NH3, which has a pK of about 36. And these are the ones that you should know. There are various others that some of them we'll discuss when we get to 2444. But this is only a very small group of compounds that you should be able to figure this out which one is the most acidic alcohol versus carboxylic acid. Those are the things that are important, and you should be able to figure the acid-base reaction. And of course, the typical acids that you have done in your general chemistry, sulfuric acid, nitric acid, hydrochloric acid. These are all negative values. HI is one of the strongest acids. These are all negative pK. Right? You don't have to necessarily know the numbers, but these are all very, very acidic. So they're all negative numbers. So is the hydronium ion, which is about -2, depending on the solvent being used. The H3O plus is quite acidic. So compare that with water. Water is about 16, but hydronium ion is about -1.7. And some other conditions it would be 0, but it is still very, very acidic. And that's the one we often use as an acid, because if you add, let's say, sulfuric acid or hydrochloric acid, a little bit of that in water, it generates enough of the hydronium ion that is being the reagent in many chemical reactions. So these are some of the acidities that you should be familiar with. And you don't have to remember the numbers. Most of the numbers are approximate, but you should know the range. Okay? All right, so going to that, now we can figure out the answer to this question. So we already mentioned the pK of acetylene would be about 26. And when it reacts with this one, what you expect to see is that the proton is picked up and gives you the anion plus NH3. And from this, now ammonia, as I mentioned, is 36. You compare the two acids, and obviously this is a stronger acid, so the equilibrium would remain on the right, because the stronger acid is going to push the reaction. So the equilibrium would remain on the right. Do the same thing with the methoxide, that is picking up this proton and giving you the same anion plus methanol. And this is again 26. Now in this case, the methanol is around 18, 16 to 18 as we mentioned, is far more acidic than the acetylene. And obviously then this is the acid is going to push on the other direction, so the equilibrium will remain on the left. And the same thing here, it's going to pick up one of the protons from this, and you have CH plus CH2 minus. This carbon has 2 electrons. And now, this one has a pK of greater than 60. This one is 26. And obviously this is much more acidic, it's going to push it towards the left, so equilibrium lies to the left. Okay. All right, going to the nomenclature question, again there will be only a few points for the nomenclature. I'm not emphasizing that, but you need to know the very basics of nomenclature. In this case, again, we have 3 different substituents here. And the numbering should happen where you get a lower number of the substituents. So from this side you have 2, 3, and 5. From the other side you have 2, 4, and 5. Therefore 2, 3, and 5 is better. So it's 1, 2, 3, 4, 5, 6. Which means it's 5 chloro, 2, 3 dimethyl, 6 carbons, so it's a hexane. Okay. The second one is an alkene, and in case of alkene, you need to, yes. What? I can't hear you. Oh, you don't, because chlorine or halogens and the alkyl groups has equal ranking. It would be different if it was an alcohol, right? Which has a higher ranking, and then we have to number from the other side. But the halogens and the alkyl groups have equal ranking. So you should know the priority rule, though, depending on the groups. We determine that. In this cyclic compound, this is an alkene, and we need to put, because halogens actually are lower rank than the carbon-carbon double bond, then we have to put 1, 2 to the double bond. So it's 1, 2, and 3. Okay, we cannot start 1 from here because the double bond always will be 1, 2. Then you get a higher number for the chlorine. So therefore it's 3-fluoro cyclooctene. And you don't need 1, 2 because 1, 2 is given almost implied that in the cycle compound. Now, this is obviously a derivative of cyclohexanol, and in this case, of course, the priority tells you that this is number 1, and regardless of which direction you go, this is 4. So it's 4-methyl cyclohexanol, but you also have to tell the stereochemistry, and the relationship between these two is cis or trans?
Cis.
Cis. So it says 4-methyl cyclohexanol. And in this case, you have, this is 1, 2, 3, and 4. Okay. And what's important in here, because as particular stereochemistry is shown, you got to figure out the R or S. So in order to figure out the R and S, you can do it with a model, or you can have your eye over here and look down this one. That gives you the hydrogen in the back, which is the lowest priority. And so we are going to see on the right side bromine, left side is the ethyl group, and the bottom one is the methyl group, right? So it's bromine to ethyl to methyl, so counterclockwise. Therefore, this is S. 2-bromo. Butane. Now this one you should be able to figure out now. We had exactly the same kind of question before. So do I need to go over that?
Yes, yes, yes. Everything. Please.
Well, like these, I would recommend that you use the model. Because you need to convert what I normally do, use the model, convert this to the corresponding Fisher form, and then compare them together. Okay, these are relatively easy to do. You should be able to do that.
Can you just give us the answers without explaining?
What?
Can you give us the answers without explaining?
Okay. What good that's going to do?
So we can
Just to make sure.
I'm not going to ask you this question again.
You're not going to ask on the final?
Okay, so if you want to verify that. Okay, so that this is S and this is also S. It's optically active. This is therefore identical. This one is both R, and the other one is, the top one is S, the bottom one is R. Again, both optically active. So these are diastereomers, obviously. The next one is actually you don't have to really determine R or X because this is actually a meso compound. Okay, so there's a plane of symmetry. So this is meso, therefore optically inactive, and the other one is also meso, optically inactive, and they are identical. The bottom one is really, again, you can figure out that they have different stereochemistry. This is R, and this one is also R. Here it's S, and the OH group is R, which means that they are diastereomers. So both are optically active. And again, with cyclohexane ring system, it's so much easier if you use the model. You'll be able to see exactly what the priority rankings are. Without that, it's very tough to do. Okay. The next question is the compound is a tertiary alkyl bromide, A, which on treatment with sodium ethoxide in ethanol is converted into B, which you can see that it's removed HBr, right? Because H13Br becomes H12. And ozonolysis of B gives C as the only product, which is shown below. Okay. Which means that the ozonolysis introduces two carbonyl groups and carbon-carbon double bond, which means this carbon and this carbon were joined together by a double bond. So we rewrite this structure so that we have 4 carbons, 1, 2, 3, 4 in between, 2. These are the 4 carbons, CH2 groups, and then we have a C, CH3, and the other C has a hydrogen there, C, H. So this is exactly the same compound rewritten. And these 2 carbons were joined together with a double bond. That's what ozonolysis created this one. And therefore we can see that that would be generated from the double bond, a hydrogen, and a methyl group. And obviously this is B. Right? And now B can be generated by elimination of H and Br from a bromide. Now it's also telling it's a tertiary bromide. So the bromine must have been attached here and not here. Okay. So that gives us the idea that it was this. So that is the only one, tertiary bromide, that can give you this upon elimination. So sodium ethoxide is an E2 reaction, NaOCH2 CH3 in ethanol gives you this, so therefore this is H. And you can verify the molecular formula of these two based on that. Right? So this question is obviously a variety of different reactions. This reaction is more recent because this is from chapter 19. And you know how this reaction proceeds. You have the carbonyl groups, which gets attacked by any nucleophile. In this particular case, it would be OH minus. So OH minus attacks either one of these carbonyl, and then it opens up it forms a tetrahedral intermediate. So the intermediate, I'm showing the mechanism, you don't necessarily have to solve the mechanism, but this is how the reaction proceeds. You have O minus and then OH. This is formed, and now this one can come back and break the bond between these two, forming O minus, and the carbonyl is regenerated, and the OH is theirs. Right? So this would be the very first step, and then this alcohol is going to be reacted with another molecule of sodium hydroxide, generating disodium salt. So you really get from this this would be the product for this. Okay. And you can straighten this out, of course, and write in any which way you want. This one is a reaction of a bromide with a strong base. This is a tertiary carbon. Therefore, the only possibility is an E2 reaction where one of the neighboring carbon has to donate the hydrogen, and therefore you generate a double bond between the two. So it can form essentially it would form the next one can generate at least two products, and of course there will be minor product, we can ignore that. But essentially it goes to a carbocation formation because the HBr protonates the oxygen, and then you eliminate a molecule of water, generates this cation. And this can generate the final product, but also it can undergo a rearrangement where you have a hydride transfer, giving you a more stable cation. And both of them will give rise to product. One of the bromide would be generated from this. Sorry, Br. Okay, and in this particular case, I want to ask you to write the major product because I did not show you the stereochemistry of the cyclohexane, and this reaction is the relative proportion is dependent on various factors, including the temperature. So since none of these were given, you just show the two products, and it can be varied depending on the condition of the reaction. The next question involves, yes?
The more stable carbon be the primary?
It probably, but as I mentioned, it is dependent on the conditions. And also what you start with, because it is also the product ratio will also change whether the OH is actual or equatorial. So because the stereochemistry is not shown, the conditions are not given, you get a mixture of these two products. More frequently, the real even product would be the predominant. All right, the next one is again protonation. And so it's a dehydration process. And in the dehydration process, the previous reaction that was shown here was E2 reaction, right? In this case, it's forming an E1 process because there is no solvent except sulfuric acid. Therefore, you generate the carbocation, which is and then these two are identical, therefore elimination of either one of those two protons would give you the same product. This one also will give you a mixture of products because it goes through a carbocation, the oxygen is protonated, and you form the cation. That cation can be approached from either direction, and you get a mixture of the chlorides. So Cl here plus and this type of problem you should show at least both products. Again, in this case, the conditions will determine what will be formed predominantly. This is thermodynamically more stable, so the first one would probably be the major one. This reaction again from chapter 19, the ammonia attacks this carbonyl group. And again, the ring opens up because and this one gets deprotonated by water. So this becomes NH2, O minus, comes back. And you can leave it like the anion, although it would be likely that the anion can actually react with either water or ammonia and transfer a proton and become an alcohol. Okay, but you can leave it either like that or just protonate that. The next one is again an SN2 reaction because you have a good nucleophile, the AMS is the solvent, and the stereochemistry of this carbon is unaffected because the attack takes place on this carbon. So the cyanide attacks this carbon and displaces the bromine. So the stereochemistry you need to show exactly like the way it is. So methyl group here, hydrogen, deuterium, and then CH2CN. The next one is from chapter, it's one of the problems from the test, from chapter 17, and it essentially shows the imine formation with the 2 carbonyl groups rather than 1. So everything else remains the same. The nitrogen adds on to the carbonyl, and then the other nitrogen. So you form 2 double bonds here and here. Right? Okay. Question 6 is write the reagents and conditions necessary to carry out the following transformation. Okay. So going from 1 propanol, which has 3 carbons, you are going to isopropyl cyanide, which also has 3 carbon plus the cyanide. So you need to have actually a derivative where at the second position, second carbon, you can do that, right? Or one possibility would be you can dehydrate this, right? So dehydrate that with sulfuric acid and heat to introduce a double bond. So you eliminate a molecule of water. Then it is easy to convert it to the bromide, and according to Markovnikov loop, bromide or iodide, either one works fine. According to Markovnikov's rule, hydrogen will be added to this carbon, and the bromine will be added there. So this will be formed, and so the next step is fairly straightforward: sodium cyanide in DMSO. You carry out SN2 process. Right? Okay, so these are like many of the questions you have seen before in your mini exams, right? So it's fairly straightforward. The COH bond angle in alcohol is closest to which one?
B.
B, 109 degree, right?
a
Because it's a
gas.
tetrahedral. The acid catalyzed dehydration of the alcohol shown below gives a major product which results from the carbocation rearrangement. Okay, so as we know that if you generate the carbocation, here you have 2 methyl groups. Now the carbocation rearrangement that will take place, so this is secondary cation, so the methyl migration will happen, which gives you this, plus the cation is here now. And obviously the dehydration means you need to remove a hydrogen, and it will be removed from this one probably, the major product, which gives you this one. So answer is 1. Which point on the potential energy diagram corresponds to the species below for the reaction of 2-methylpropene with hydrogen chloride? Okay. So 2-methylpropene is this. Right? And so the hydrogen chloride, the way the reaction goes, is protonates the CH2 first, following Markovnikov's rule. And therefore, what you see is really the transition state, where it's H and Cl. So this one attacks and leaves. Therefore, small negative charge is generated in the transition state on the chlorine, which this bond is breaking. And this bond is forming, and this double bond is partially becoming a single bond. So this is really the transition state structure for that, which means that this is the stage that indicates